a solution to the wave equation over here according to the rule psi of z, excuse me, psi of, my bad, phi of z, you know the drill, is psi of f of z. That will still make sense because guess what? The A calculus has all of your favorite rules of calculus. You've got the product rule, you got the quotient rule, it's linear, the chain rule still works, all of that stuff. Power series still work, calculus works with variables over an algebra. So I could try the method of conformal mapping to try to like find weird solutions to the wave equation. This is an open problem for me right now. I have a student working on this, kind of. He's not a math major. Well, is he? It's debatable. He doesn't deny that he's a math major, but he's taking computer science classes almost exclusively next semester. So what does that mean? I don't know. It's not a good sign. But he's a good student. No, it's not Anthony. But Anthony has other problems. But sorry, I think I spent too much time around Dr. Sperano. I have like some sort of like, you know, if Sperano identifies a target, I feel some sort of like, you know, what's the word? Fraternity of trolling. What's that? Bullying. We do need more bullies. Bullying.
I need to be bullied in order to become the mathematician that I was supposed to.
I mean, I think it was a very good thing that like when Dr. Skamordis was in school as a child, he feared wearing the dunce cap. That's like a good thing. Do your homework, otherwise you'll have to be, if you're the last in the class, then they put a silly hat on you, and you know, I don't know. We're so far away from that at this point. We're so far away from that.
That would be motivating.
I mean, good grief. Anyway, the closest I ever experienced to that was I had a linear algebra teacher who turned back tests in the order of the grades, highest to lowest. I think I told you guys before. I tell this story fairly often because it amuses me. But anyway, my point is you could do the conformal mapping thing over an algebra. Now, so in order to do this, I need to come to terms. See, so in order for conformal mapping to work for complex numbers, I have to have complete mastery of how curves map to curves under the mapping F, right? And thankfully, it's conformal, which means perpendicular maps to perpendicular. That ain't the case for a hyperbolic map. Hyperbolic maps do all kinds of wacky stuff. Like I don't begin to understand the geometry of what's going on with hyperbolic maps. Even simple things like the squaring map do weird stuff to circles. All right. So he's building a web, like my student who's building a web tool where he actually feeds in, he like pictures the z-plane and the w-plane at once and like feeds it a grid under like say the square map and the hyperbolic and sees where the grid goes to from one to the other. So like visualizing it. So that's he's working on that right now. He's going to give a talk this Saturday actually on this thing. I hope well anyway, it looked good. But all right, so that's one idea. Now, I think I have just enough time to get into trouble. Yep.
When did you give? What time is the talk?
Oh, not here. It's at Hamden Sydney. It's in Farmville. It's like Saturday at like 4:30 or something. If you're interested, I'll tell you. What?
AM.
AM? No, I wouldn't be there. You're kidding. No, afternoon. All right, so anyway, my final thing I will share with you is one thing I have discovered with a student in like the summer of 2016 is how to use this algebra stuff to solve the arbitrary nth order homogeneous differential equation with one overarching method. Would you like to see? So like, let's see here, example, and I won't tell you it in general, I'm just going to do it, okay? Suppose I want to solve, and I'll start with a really dumb example, y prime 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 equals to 0. Now you guys already know how to solve this. You just integrate 3 times, right? No big deal. But I can also solve it like this. I'll say, oh, okay, so my characteristic equation is alpha cubed equals to 0. So if I look at e to the alpha t, that's really 1 plus alpha t plus 1/2 alpha squared t squared, and then everything past that's 0. So the component functions are 1, t, and apparently 1/2 t squared. Therefore, my general solution is c1 plus c2t plus 1/2 t squared, c3 t squared. Linear differential equation says you have to take, linear combination of your fundamental solution set. What I'm arguing is that we can see the fundamental solution set in the component functions of the exponential over an algebra. What algebra am I using here? So this is in, let's say, A, which you could write as the following. It's R of alpha quotient by alpha cubed. So I'm modding by the ideal generated by the cube of alpha. This is a quotient space of polynomials. It's also a three-dimensional algebra with a nilpotent generator of order 3. Example 6. Okay, great. How about y prime prime minus y equal to 0? Oh, okay. So this time, my characteristic equation is alpha squared minus 1 equal to 0. And I'm going to work in the algebra, which is r of alpha mod this alpha squared minus 1. In other words, I am setting in this algebra alpha squared equals to 1. In my algebra, my characteristic algebra to this differential equation, I have alpha squared equals to 1. And so my solution will be seen from e to the alpha t. But this time, what happens if you have alpha squared equals to 1? Well, if you look at it, you got two things, right? You got some k equals 0 to infinity of like alpha to the 2k over 2k factorial, and then you got your times t to the 2k, right? And then my odd terms. So what I'm doing here, guys, is I'm just assuming that the power series for the exponential, it's still legit in our context. It is. I've proved it. I had a student write a paper about it. It's all worked out. It's all copacetic. And so what's the deal? Alpha to the 2k is what? See, we have alpha to the 2k is 1, and alpha to the 2k plus 1 is just alpha. So what you got here? You got yourself cosh t plus alpha sinh t. Usually when I write this equation, it looks like this. E to the jt is cosh t plus j sinh t, which I also thought was like super cool when I first found the hyperbolic numbers. The fact that that's the imaginary exponential. Cosine and sine get replaced by cosh and sinh. Chills, right? It was really, really cool until my students found it was on Wikipedia before we found it. Arrgh, stupid Wikipedia. We're not the first people who've played in this playground. In fact, generation after generation of mathematicians forgets this. And then the next generation forgets it and fails to publish it and propagate it to the next generation. It's a time-honored tradition for probably about 5, 6, 7, 8 generations of mathematicians, because this stuff was discovered by like William Cockle or something in the 1830s. It's about the same time as the Quaternions. Anyway, so guess what? General solution is c1 cosh t plus c2 sinh t. One more example, and then we'll call it a day. Do you guys remember in differential equations how you solve the repeated root case? I might get stuck on this, so I hope you guys can help me. Example 7. suppose we're up against like y prime prime minus, let's say, 2y prime plus y equals to 0. What's my characteristic equation this time? It is alpha squared minus 2 alpha plus 1 equals to 0. In other words, I want to work with a algebra unit alpha such that alpha minus 1 squared is equal to 0. So I look at e to the alpha t in this context. The question you have to think about is how can you make use of your defining algebra? What should I do here to make use of my alpha minus 1 squared being 0? What should I do? One of my favorite tricks, right? I subtract 1 and right, like that. And that gives me e to the t, because the laws of exponents still work. And then I've got e to the alpha minus 1t, which then we use the power series expansion for exponential, which is 1 plus alpha minus 1 times t. And then that's it, because alpha minus 1 squared is 0. The exponential truncates there. And then just look at things here. So what do I got? I've got e to the t minus t e to the t plus alpha times t e to the t. So that gives me the solution y is equal to c1 times e to the t minus t e to the t plus c2 t e to the t. Now that's not the standard presentation of the solution, but that's the solution to the repeated root case. We can do this all day long. This will solve any nth order differential equation. Up to your ability to, like, sort through the algebra and stuff, obviously, but this, the real case, the repeated root case, the complex case, all the same thing. The other thing is, what we're doing, it works just as well if you're dealing with an nth order differential equation over an algebra. You can look at the extension algebra of that algebra and you can still solve it. Right? Anyway. This probably won't help you with the tricky homework at the end of the homework, but there's something I got hung up on a couple days in there. I hope you guys can see through it. I'll help you if you get stuck. Anyway, have a good break, guys.